Right, I think we're probably kind of coming towards the end of this. Feel free to keep, if you're still going through these, keep playing around while I'm talking if you like. I'm going to run through the rest of this notebook, and then I might go off on a couple of tangents, just talk a bit more about the dashboard. And then when we get to the bottom of this notebook, we'll probably have like a 15-minute rest break. Go and there's coffee and stuff outside. So let's go through the answers to these exercises if you've been running through filling these in directly. So the first one was how many rows are there in our data set? So this is effectively doing a length of our data frame. And you can do len DDF on that. Oh, my kernel's dead. I won't run those cells. No, I will. Let's restart this. Sorry, I probably just need that. No, need my imports. Okay, sorry, I think I'm back there. So yeah, the first was doing a length of the data frame, see how many rows there were. Not quite sure why that is dead. There we go. So we'll talk a bit about the dashboard in a second, I think, because it feels like a good time to talk about that. So the next one was how many non-cancelled flights were taken. So you can do this with like a standard selector in Python, use your square brackets, and then we want the inverse of the cancelled column. And again, taking a length of that. So if you are familiar with pandas, this kind of stuff should feel really familiar, right? But you can just see that Dask is breaking this down into all these chunks underneath. Next one, in total, how many non-cancelled flights were taken from each airport? So again, we've got like a much larger panda-style operation. It's using that kind of dot notation chaining of operations here. So you're taking this not cancelled data frame, grouping it by the origin, taking that origin series, doing a count, and then all of this up to this point would be this kind of lazy operation. Dask would create a task graph and then sit and do nothing. It doesn't know if you want to do it. So we've got this dot compute on the end just to kind of make that happen for you. Next is what was the average departure delay from each airport. So again, it's doing a group by, taking a column and taking a mean. My flight was very delayed yesterday, so maybe it's in this data set. Next one is what day of the week was the worst average departure delay. So you can use the IDX max. We have really strong coverage of the pandas API. There are a few things missing. I should try and find one of my colleagues in Rapids. Slight tangent. I'm doing a tutorial tomorrow about GPU accelerated compute, and we have a GPU pandasy kind of thing. Plays really nicely with all of this. So if you're interested in that, you should come to that. But that library is implementing the pandas API, and Dask is implementing the pandas API, and we started creating some nice visualizations recently of API overlap to see kind of how much of the coverage we have. So we have these kind of status boards that we can keep on top of and kind of see, how much are we moving towards 100% API coverage. So when I swap over and somebody else talks, maybe I'll dig out those links. You might find that interesting. And then the last one is let's say the distance column is erroneous, and you need to add one to all the values. How would you do that? So we can use, oh, my kernel died again. I don't know why my kernel keeps dying. It's not doing anything. Okay, I'll go through and rerun that again in a sec. But we're using .apply here, right? So we can pass our data frame a function. It's just a little lambda function in here. We're passing it a function to map across our code. And again, Dask can kind of handle just breaking that out and running that across. So let me restart my notebook and kind of come back from the beginning, and then we'll move on to the next bit. Actually, no, before we go into the next bit, let's do some more dashboard stuff, because I think folks, I've seen a lot of you kind of setting up the, sorry, my kernel is just completely gone. Oh dear. Oh, sad. Oh, really? Okay. Okay. A whole binder's gone, yeah. Right, let me restart my binder. Um, yeah, that's a good idea. It's undistributed, right? Or is it docs? Dashboard. Yeah, okay, so let's talk about the dashboard a bit. So I think you've probably seen up until this point that you've got kind of standard Python code that you're writing that's following these APIs that you use, and then you've got this kind of slightly more abstract Dask cluster thing, right, that we're creating in various ways. We're going to create it in a bunch of different ways. But we have like this client, we have this scheduler, we have these workers, and we're kind of giving it code and data, and it's doing stuff, and then when it's done, it's giving us results back. And so that can be strange, especially when you're in a situation where you run some code. You might have found it in the first notebook, actually. You run one of those cells, and it just hangs, right? And you get the little star in Jupyter, and you're like, what's happening? What is my cluster doing? Is it okay? Is it happy? Is it healthy? Like, you've got this added layer of complexity and this abstraction on top. And so I think it's important to have a good overview of what's going on. So we both have a dashboard, which we'll kind of dig into. Like, I think I'll go through like a whole bunch of the plots so we can see all sorts about what's going on. But we also have other like UI elements where we're trying to expose information to the user. So the first one kind of showing up here is we have these like HTML wrappers. So if you're using Dask in Jupyter, if you create a client object, if you create cluster objects, they'll give you a bunch of information about the cluster. They'll give you information about the workers. You can click where it says cluster info and it like drops down and expands. You can see the scheduler, you can see the workers. I don't know if there's not more of that, but you can get like a bunch of information about what's going, like what kind of cluster it gave you, which is really helpful. But one of the most helpful things is it gives you the link to the dashboard. Now, when you run the Dask scheduler, it listens on port 8786 for like Dask related things. That's like a TCP port. And then it listens on port 8787 with this web server that's running the dashboard. So Dask always starts these two ports. A lot of deployment around Dask is just like, how do I get to these two ports? Because I care a lot about these. So it'll try and do its best to like figure out where it is. If you're just running locally, it'll just give you localhost. If you're deploying on like a more complex environment, often this link will reflect the like current location. Apologies, the binder one was a bit broken. When you click that link, it opens up the dashboard. Oh, I'm back into Jupyter Labs. Let me just run a bit in here and I'll get the actual dashboard alive again. Yeah, okay, so I said you can click this cluster info and you can see all information. So the client connects to a cluster, which connects to a scheduler, which connects to workers, and you can kind of drill all the way down and see everything you want to know about the cluster. But the main thing I want to show you here is the scheduler has a dashboard, and we'll talk a bunch about that. The client object tells you where that is, the cluster object tells you where that is, the scheduler object tells you where that is. And then also the workers have a dashboard as well. So you can see on like a worker by worker level, what is this worker doing, what tasks does it have, what is the state, and you can click these links and view those. Now, if I pop open the dashboard again in here, I'm having to change things because Binder is proxying things for us, and I have to go through that proxy to view stuff. But we basically, we have this website, right, that you can go into for your Dask cluster and poke around and see what's going on. There's also some routes on here that kind of describe, these are all the graphs I have, these are all the different plots that are available, and this is what Jupyter Lab and the Dask Lab extension is kind of plugging into here. So if we give this URL here, it's gone and got the list of what are all my plots, and I can kind of grab those and rearrange those and do whatever I want. But rather than opening a million plots in Jupyter Lab, I'm just going to go through the web page. But just so you know, there is like a one-to-one. You can get all of the plots either way. The website also gives you like some aggregated view pages. So this is like the main status page. It's got the task stream, it's got the progress bars, it's got a number of tasks and memory and kind of like a high level view onto what is my cluster doing. often this is like a first point of call of, I'm going to go and run some Dask code, and then I'm going to look at this to make sure that I am dasking, right? My code is actually running on the cluster, stuff is happening. But then once you've kind of got that reassurance that things haven't hung and you are just waiting for your computation, then you can start drilling around in this dashboard. So let's have a look. Let's run a thing. What did I miss then? Right, there we go. So we can see the dashboard doing some stuff. Now we can see up at the top we've got the total memory being tracked by the cluster and the amount of bytes being stored per worker. It's not super clear here, but you can see we're tracking like a various memory statistics. So we're tracking the data that Dask knows about. Right? These are the kind of inputs and outputs of those functions. Dask keeps track of that memory. If it starts running out of memory on that machine, it will start swapping that to disk automatically. Like Dask will do that before the operating system even kicks in and starts doing that. And you'll start seeing these bars go orange. And that means that, oh, I'm shuffling stuff onto disk. We're not going to have out of memory errors. Things are probably just going to slow down depending on the speed of the disks that it's swapping out to. But you can also see we're tracking unmanaged memory. So this is kind of stuff that's happening outside of Dask's view that's maybe you've submitted a function, that function is allocating some data by creating an object that's maybe not immediately returned, or it's causing some kind of side effect that's creating some data outside of Dask. That can mean that we start running into issues. We're trying to track all of this memory so that we can still intelligently swap, but occasionally you can have leaky functions still that start creating memory that we can't clean up or we can't keep track of. And so being able to just come here, if you see out of memory errors or if you see anything along those lines, this is a good place to come and see, when I run my code, do I get this, oh, it's gone again on my thing. You get this little faint blue bar that starts to grow on the end of this, which is unmanaged memory. That's one of my favorite uses of this plot. That's really helpful to see what is happening in terms of RAM usage. You've got all your bars about how much CPU utilization and how many tasks are processing and everything, which is useful. And then you've got the larger task stream here. So there's a few different colors that are worth knowing about within this. So the plot for the tasks is just using a standard color scheme. So I think it's just using Viridis underneath. And so your tasks will just be assigned a different color. You can kind of get a visual overview of, oh, this is the read CSV task, this is the select, count, this is whatever. But also, when the workers move data across the network between each other, you'll see red blocks on this. So you can see I did a length, so it would have done a length on each partition and then an aggregate length. And in order to do that aggregate length, all the workers had to pass that memory to one worker to aggregate them. And you can see the little red stripe at the end, which is just, this is network access. We're moving some memory around. If you run some work and this starts going really, really red, that's bad. The workers are getting really chatty. They're moving a lot of memory around. It's a point where you need to start thinking about can I do this in a way where I don't need as much communication? Is there a bug in Dask? Is there something wrong with the collection? Is that you shouldn't be seeing too much red there. We also see when you start moving on using more high-performance networking that these kind of shrink down, which is great. And I'll talk about that in the deployment bit later. The other color, you'll see orange in here. You'll see orange blocks as it's swapping to disk. That's kind of an operation the worker has to wait for stuff to move to disk, has to wait for stuff to come back. So you'll see orange chunks coming in there if you are reaching your memory limits of each worker. And then the big scary one is when you get a big black bar. And that means that the worker had an exception that it couldn't progress from, and it's probably stopped, and you probably got a worker killed exception or something more sinister coming up in your notebook. But you'll get a big black bar of the worker tried to do this task and it couldn't. And I think, let me just, I might just do client sub. No. There, big black bar. Right? I tried to import a library that didn't exist on the worker. There is no way for the worker to progress at this point. So this is the kind of thing where you need to come back and have a look. I think if I probably get the result of this future I'll get the rest of the traceback from that. No, I didn't. No, oh, I didn't even look at the stored result. Anyway, I'm kind of flitting about a bit, but this is a good place to come and see, okay, something's gone really wrong. I've got a big black bar. I need to go and have a look at why has my worker died. We have quite a useful documentation page on Dask worker why killed, something along those lines. This one, why do my workers die? Yeah. So this page kind of talks through standard situations. The most typical one is that your Conda environment or your Python environment is not consistent between where your client is and where your workers are. And so you're probably importing packages, wrong versions, or missing packages, those kind of things. But there's also various reasons that can happen. This is a useful page if you start seeing black bars and worker code exceptions. So the other thing we can see is we can see the workers themselves. We can click this workers tab. We get a list of our workers. We can see what their CPU utilization is. We can see what their memory usage is. This is really useful, especially when you're deploying onto like remote clusters where you don't necessarily have, on your local machine, you can open up the task manager or do top or whatever. On remote clusters, this is a great place to come and see your overall CPU utilization, memory utilization, etc. Now we also have a tasks page. This is just the task stream from before. Was this? Can you get the task groups on this one, or is that? Oh yeah, I'm jumping ahead. Okay, I'll come to that. We also have a system page. This is showing us the system utilization of the scheduler itself. So if you want to know if the scheduler is becoming overwhelmed. The scheduler works well with graphs that are kind of up towards like 1 million tasks. When you start reaching beyond that, that might just be too much for the scheduler itself to handle. So you can start to come in here and see, oh, the scheduler is overloaded. It's kind of backing up. It's not giving enough work to the workers, that kind of thing. The profile is, I would argue, the most useful page in the dashboard in that it gives you kind of some diagnostic information into the code that you ran. This is a flame plot of the code that we ran. This is probably the length that I did. It's kind of whatever the last graph that it executed. It's got all the timings because the workers are executing those functions. It has the timings of all of those function calls. It will feed all of that back to the scheduler. So you can come in here and see what is taking the time. When I run this graph, it takes 40 seconds to run through the graph. Where is time being spent? What is going on? And you can kind of hover over and see, oh, this is our read CSV here. You can see we're doing an open file. This is happening within FSspec. And then here we've got our, this is the read. Oh yeah, so this first one is to open the file. And I think because we're reading from like a remote file system, this took a little while. And then we have our pandas read here, which is doing our read CSV. It should be, where is it? Read CSV, yeah. So you can see this is kind of what's taking the time. And as you kind of drill up, you can drill in and see what calls is this function making. You kind of get a good view of what's going on. There's probably got our length at the end here, yeah, safe size of. This is really useful to come in and see, oh, I've got this really long block here. What is this? What's taking the time? Can I tune my code to kind of work better in this situation? So I think when you're really trying to squeeze performance out of this and trying to how to speed things up, this is a good place to come to see what's taking the time. So we also have this page, which I should probably do a more interesting graph to make it do something better. Okay. Shall I persist like one of these? We haven't talked about persist yet, have we? Okay, right. I won't preempt persist. But yeah, okay. So we can see here we have our. This is a high-level view of the graph that we made, right? So if I call .visualize on that object, we would see that kind of inline in the notebook view. This is our task groups. This is a high-level view of what's going on. So these are the things that I've created. Should there be text on these? Yeah, okay. Okay. Okay, we should fix that. But this is giving us like a high-level view. So, in the graph, well, let's look at the actual graph, right? So we have this graph page where we can see the graph itself. This is the same kind of thing that we saw plotted out with GraphViz, but just kind of on its side in bokeh. So we've kind of got our read CSV tasks down the sides, and then our kind of our aggregation steps as that graph comes together. But then this groups page shows you Still, each one of those layers, right? You've got our ETSV layer and our length layer and our final result. I think this had a group by in it as well, right? This one that I was doing. And so this is just showing us the individual blocks. This is showing you like the workflow as a diagram. We'll have a look into why this isn't quite displaying properly. But this is a good place to come in and just see what kind of graphs have I created, what is the scheduler working on at the moment. You can see we've got the statuses of each of these tasks. So this one is, some stuff's being held in memory. This one's errored for some reason. But yeah, these are useful graphs for getting an overview of what you're running. And then we also have this other info page. Now, I find this most useful to jump to the worker dashboards from here. I don't think that if I click them, they're probably not going to work in Bokeh, in Binder. But it is a very similar visualization to this. You can see what's going on in the worker. You can get a whole bunch of stats about the worker. And then we have this more list. Now, this is kind of all of the individual plots that you find in Jupyter that you can kind of click and drag and move around. You can also get them in this dashboard and open them as full pages if you want to just open a bunch of windows and rearrange those, right? You're not limited to just using Jupyter. You can use this however you see fit. But if we want to just open the graph in one panel, we can do. We've got all these kind of individual pages here. Yeah, so worker memory. We can open up a bunch of panes and view these if we're not in a Jupyter environment. So hopefully that's kind of giving you a little bit more insight into what the dashboard can kind of give you and the powers of it. And this is why through this whole tutorial we're kind of doing Dask distributed, which is not always necessary. Dask does work. You don't have to create the client. You can just use Dask. It will use a little threaded scheduler, but you don't get the benefit of this dashboard. So I tend to advise to everybody, use distributed either way. The performance is roughly the same, and you get these kind of added benefits here. So let's dive back into the more DataFrame type stuff. We'll run through this notebook, and then, as I said, we'll do a rest break at the end, go and get some coffee. So is this the persist bit that I preempted? No, okay. Okay, anyway. As we were running through this notebook, we kept running through the same chunks of the graph over and over. So sorry, I'm just trying to remember where I am in this notebook, but yeah, no, that's fine. We're running the same things over and over as we were running through this notebook. But really, we kind of want to be storing the outputs of these things before feeding into the inputs. So when we've been chaining stuff together, let's find one of the big chaining things together. We've got this data frame that we're calling a group by on, and then selecting a column, and then doing a mean. Each one of these intermediate steps will give you this lazy Dask object that's not been computed yet, it's not been evaluated yet, and we can store those as we're going through. So here, if we just take the not cancelled flights, and we can assign that to a variable not cancelled, and then we can use that later on and build more on top of that. So then if we're going to select the depth delay column and do a mean on that, we can assign that operation to mean delay. And then we could do standard deviation as well. And if we run this, that cell ran almost instantly because these are all kind of lazy objects. These are all lazy variables that I've got stored. And then I can see what it's like to actually run through and compute those. Let me go to the graph again. I think I've maybe not run all the cells in my notebook, and that's why it's not happy. Yeah, there we go. All right, so this, actually running through and doing that calculation took the time in that operation. The other thing we can do is if we've got these kind of lazy objects, we can call .compute as we have done, but we can also use the Dask client to compute that. We actually use the Dask API here, but instead of saying .compute of this thing, we say compute, please can you compute these things for us, right? So we have a Dask.compute call here, and this is kind of a way that we don't have to wait for each one sequentially. We don't have to call compute, wait for it to finish, and then call compute on the next one, wait for it to finish. We can just say Dask compute, please compute the things, and it will run that. So if we run this one, that ran faster. It was able to do more concurrency because it's trying to evaluate two lazy Dask objects at the same time. So it takes kind of roughly half the time. And this is because the graphs were actually merged together at the point of execution. And because there's kind of common operations in there, we can reuse those as well. We can visualize all of that together. Well, this is using the new visualization engine. So we do have, this is like using an experimental. We have this Cytoscape engine that is not using GraphViz, it's using a different engine, and this is showing us merging those two together. Yeah, is that? Oh, yeah. Yeah, so I have to like do two-finger drags and stuff, but yeah. Oh, you can, oh, nice. I've not played with this much yet, actually, because the graphs that we've seen so far are just use GraphViz, and they just spit out a PNG or an SVG, right? And we were kind of doing two levels of zoom. You just click on it to make it full size or not. Whereas this is using the new Cytoscape engine where you can actually get the graph and kind of zoom and plot and drag and move stuff around. So, yeah, okay, so persist. So as well as running through, so far, we've made some lazy objects, we've created variables that point to those lazy objects, and then we've told Dask to evaluate those, and that gives us the result. Right? But then the cluster kind of forgets everything that it did. Right? There's kind of run through all these operations. The operations have got these intermediate steps, and all of that intermediate data kind of evaporates as it moves on. Right? It doesn't need to keep track of any of that. But sometimes it is valuable to you to say, I want you to run up to this point and then store that result, and because I'm going to build on top of that, but I'm going to tweak a cell and run it, and I'm going to tweak a cell and run it, I'm going to tweak a cell and run it, and I don't want to do the load every single time. And I've maybe done a filter or something at that point. You might want to just say, okay, get all the way to here, and then pause, keep this stuff, and then I'm going to kind of iterate on top of that. So you're almost like extending the graph on in various ways. And to do that, we use .persist. So this is kind of the counterpart to .compute. Instead of saying, run all the way through this and give me the answer back, you're saying, run all the way through this and remember the answer for me. So if I take, again, we'll take our not cancelled flights and filter by flights from JFK. We could do like a mean and a sum on each of these. And this is going to run all the way through that graph. I should reopen, actually. Maybe I should open the graph one here so you can kind of see. Oh, that's my random future, isn't it, that I had hanging around. Sorry, let me just try and delete that. Did I call it foo? No. Where did that persist go? A, that's it. There. Okay. What was that? That was foo. Jupyter holds onto references to things sometimes. I think I can't get rid of that one. But if I run through these operations, that was very fast, but it made two separate graphs, right? Each one of these, this mean and this sum, is built on top of this operation that's already happened, right? We've already got this inversion, we've got a filter, some filtering, and then we've got a selector of, like a where here. And so doing mean and sums went start to finish on that graph both times. And it took, half a second to do so. But what we could do is we could take just the results, this JFK results, and we can say persist. Right? So instead of having a pointer to a graph that would run this thing, we have a pointer to a graph that would run this thing plus the intermediate result of that. So if I run this cell, you can see the graph has popped up. It's done this first operation, and now it's sitting and waiting. The workers have all of this data in memory. Now, obviously, this does eat into your memory of your cluster. You have to be cautious about not running out of memory if you have like lots of different steps persisted. But now if I do my mean and standard deviation, it goes much faster because it hasn't had to recompute this chunk of the graph, right? It's just building on top of that graph each time, which is much faster. So, yeah, okay, so we'll move on a bit now into kind of running your code with these data frames. and how to like kind of, this is starting to peek under the hood of how these things work and how to kind of access these objects underneath this abstraction layer that we're providing. Dask doesn't cover the full API. Like I said, I'll try and find those pages that show how much API we do cover, but there are just things that will be never covered. They don't necessarily make sense in terms of how we can implement them. They're not necessarily distributable. And that API is also just huge and it moves fast, and like pandas is this vibrant, amazing, big project, and it's hard for us to kind of keep everything up to date. So sometimes we just say, this is not implemented and it's not going to be implemented, and if you want that feature, you can kind of do it yourself, and these are the building blocks, the bits and pieces you need to add yourself. Or you may have some specific nuance to how you want something to be done, and so you can do that yourself. And so by doing that, we have a few different methods that we can call on the data frame, which allow you to effectively map a function over the like layer below. So this Dask data frame is many pandas data frames, and our operations are kind of running on top of all of those. But we do have this map partitions function where you can basically just pass Dask a function and say, on each partition, please run this function. And so you're kind of operating on all of your chunks. If you've got 10 pandas data frames that make up your overall data frame, that will just be run on each of those pieces. And that can be a really nice way for you to kind of express your own custom logic, passing things through into here. So here's an example. Let me shrink my graph down a little bit. So we might have here where we have this custom converter where we're going to take our DF, this is our pandas partition, and we're going to multiply it by a specific number. So if we have a series here, we're just making the meta here. This meta is because we have to tell it what the D type is, isn't it? Yeah, so because all of this is happening lazily, it may not know what our D type is. So we have this kind of meta option that you can pass in a data frame that looks like your data frame, and just can give it this metadata. So we're setting the D type here. So we're going to take our distance series, and we're going to call map partitions and map our custom converter over that. And we're going to say, I want you to multiply everything in here by 0.6. Here's the meta object, so you know what it looks like. And we'll get back this distance km object. If we look at the visualization for that, does that go bigger? Yes. We can see in the graph, we've got our read CSV, we've got our get item, which is selecting our column, and then we have our function, right, my custom converter. We're passing this function straight through. This is kind of how you append the graph yourself if you want to do stuff manually in at this point. And we can call head on that, which will show us what the result is. I preempted that. So yeah, there's more information about what that meta does at the end there. There are also some other functions up here that are kind of mentioned. So as well as doing map partitions, you can do map overlap, where you kind of have overlapping rows from neighboring partitions if if the boundaries cause you a problem in what you want to do, and you need to read a few either side. And we also have a reduction if you want to do custom reductions where you're doing those aggregations yourself. So with all of this, you can load in your big distributed data frame, and then you can write really custom and bespoke stuff if we don't have the pandas API compatibility, or you want to do something very specific there. So yeah, that's the end of the data frame section. So thank you all for being awake still, which is great. It's yeah, any questions? Go for it. Yeah, sure. So the question was, there's a lot of similarities here with PySpark. What are the kind of differences, and what are the pros and cons to using each one? So yeah, sure. Yeah, yeah, absolutely. So yes, Dask does do that. Dask kind of does all the same kind of things that you would get in that. I think the deployment section might kind of clear some of that up. You can also run Dask. If you have a Hadoop cluster with Yarn installed that you might be using for Spark or whatever, Dask can also leverage that same hardware. So if you've got that, you can try out Dask. There's a great documentation page here comparing Dask to Spark. There's like a whole load of stuff in here that you can kind of read in your own time, but the few things I would say is Dask is like this low-level building block for building out distributed Python. It's written in Python for doing Python stuff. So we have all this DataFrame stuff, which has a lot of overlap with PySpark. But also we have this whole like array implementation, and we have all these other things that have kind of been built out from this kind of ground point. So there's a lot of stuff that you can do in Dask that you can't do in Spark. But there's also, Spark is very well tuned and very, optimized for its use cases, and we kind of get it going in that direction. I think one of the reasons when I was working in weather and climate, I evaluated Dask and Spark at the same time. And one of the big things for me was just when something goes wrong in my Python code, I do not want a Java error message. I don't write Java. I don't like Java. I do not want Java stack traces. And I'm going to have to hand this to somebody who is, I have a software development background. I'm kind of comfortable with these things, but I'm now going to hand this technology over to somebody who their job is geosciences, and maybe don't necessarily think of themselves as a programmer. Programming is just a tool to do the thing that they want to do, and the last thing they want to do is be like, what is this Java stuff? PySpark has moved on a lot since then. I think you get much more nice error messages now. But it's the ecosystem of Dask is built within the PyData ecosystem for the PyData ecosystem, and it plugs in natively, whereas PySpark is kind of this compatibility layer almost. There's like a whole other bits and pieces in here about these kind of things, but they're both good options, and they've both got pros and cons. I think Dask is kind of going for this more integrated, more flexible package. But it does mean that we're trying to add features that have been in Spark for a long time, right? Like Dask SQL is a relatively young project. Like Spark has had a SQL engine for a long time, whereas Dask has only kind of more recently got like powerful SQL. I think, like Charles, when did the predicate pushdown stuff go in? Yeah, like a month or two ago, Dask SQL got predicate pushdown capabilities so that it could kind of optimize graphs and squash things down. That's not been there. That's been in Spark for a long time. So we're kind of catching up with some of those things. But it's kind of the flexibility of, if I want to start with Dask, I can grab my laptop, I can install Dask, and that's it. I don't need a cluster. I think going from 0 to Spark is like a big step, and often involves getting IT folks involved, and there's like a huge amount of setup around getting like a functioning production-ready Spark cluster. And it's hardest to dip your toes into, whereas Dask lets you go from like my laptop to a bigger machine, to a couple of machines, to a supercomputer, to the cloud, to wherever, right? And you can kind of scale from 0 up from there. So I hope that kind of answers it, but please do go and check out this documentation page because it's got like a ton of stuff in there. Cool. Was there any more questions before we take a break? Yeah, go for it. Sure. So that each Dask worker creates like a local file system space that it can use, mainly for the swapping that I was talking about, right? When it runs out of memory, it will start swapping stuff to disk, and the worker has a space that it does that. By default, that is just the current working directory. It will create some worker directories, and it will start swapping into them. I don't know if I can, yeah, I can see it here in my little browser thing. This is the Dask worker directory. You can see there's some log files in there. Commonly, when you set up Dask, again, we'll talk about this in the deployment bit, but if you're running on like an HPC, you might have some scratch space, some temp space that is for that kind of writing, and so you would just configure and say, workers, you should put your stuff over here. That's kind of mostly what that is for, in terms of, other than operating on the data on the file system that you're telling it to do, like read CSV and 2CSV and things. It's all kind of for doing this memory management, swapping in and out and stuff. So you can use like Unix sockets to communicate between the processes rather than, by default, all the workers use TCP to communicate and kind of go through the network stack. You can use Unix sockets if you prefer. Obviously, that restricts you to the machine that you're on. but that is a thing as well. So you can use the file system for that. Yeah, go for it. I mean, yeah, in the deployment bit, I think we're going to talk about multiple clusters and how things kind of work. But the way that we've set things up in the notebook so far is it's launched for Dask workers. They're communicating with each other in the standard way. We're kind of, we're limited by the binder environment. You're all limited by the laptops that are in front of you for within this tutorial. But using Dask feels the same, whether you started one Dask worker on your laptop or a Dask worker here and a Dask worker there. Everything will operate the same. The dashboards are the same. It's just the actual deployment of how do I run these things, and we'll go through that in the deployment notebook. Cool. Okay. Well, let's give it like maybe 10 minutes. Everybody go and get a coffee and have a rest break, and then we'll come back and go through the array notebooks. This is the like NumPy flavored bit of Dask.
Oh, that's loud. Okay. So going back to the analogy, so imagine that you're building a house and you have to put like on a wall like a bunch of bricks. And if you have every person bringing one brick, and then the back and forth of bringing that brick is going to take a long time. While if the foreman says, hey, why don't you all get like a, how you call those stuff that you put things? A wheelbarrow? Yeah, a wheelbarrow. So you get a wheelbarrow, and then you can bring like more bricks, and then you can put them on the wall, and then you can go back and forth. And so that's kind of like the idea of if you have like a too small of a problem, and then what every worker or every person like bringing one brick, then this is going to take a long time. We're going to get it done, but it's going to take a long time. Now, too big is also a problem. If your chunks are too big, this is also a problem because you likely will run out of memory. Like, the way I like to think about this, like maybe it's just like too heavy for that wheelbarrow to carry, and then like you're gonna kind of get stuck in there, and then you're gonna kind of have to rest, or then like you're not gonna be able to push it all the way. So you will start seeing that the dashboard data is being spilled to disk. Well, it's gonna start seeing gray on the dashboard, on the memory, and then it's kind of like gonna take longer time to process that. So in general, like there are a couple of rules of thumbs. Like that you can take a look and then see, depending on your application, what to do. But users in general have reported that chunk size smaller than 1 megabyte, it just tends to be too bad. It's just too small. And it goes, a good number is something between 100 and a gigabyte. So that's also, it's good. But if we go over that, it tends to be like just overloads the memory, and we don't want to be there. The other part to take into consideration is like, as an upper bound, we want to avoid very large task graphs. So when we were looking at the number here, or the amount of tasks, we don't want that number to be too big. So something between 10,000 and 100,000, it's okay, but like after that, it might start like being bad. And then as a lower bound, you want just to get the number of chunks to at least equal the number of workers that you have. So if you have like 4 workers, let's just get at least 4 tasks, and then ideally multiples of 4, that might be good. If you get way too many, then that might be a problem. And if you have only 2, then trying to kind of like, if you have, let's say 4, and you choose 3 chunks, then there's going to be 1 worker that is going to be sitting there doing nothing. So you kind of want to like take into consideration that. And there are like other considerations that go into trying to align the data with the chunks and how you read that data depending on the formats. So in general, in multiple applications, you're not going to be creating your Dask arrays, right? So you will read your data from some format. Usually there are like good formats that are already chunk data, like ZAR, Net, CDF, TIFF, and you want to like kind of like check, okay, how those chunks look like, and then how my resources look like, and then trying to accommodate for that. There's a lot of readings on how to choose chunks and arrays. I'll consider you to like, if you are in a field that deals with arrays, go to the documentation. For now, we're going to do like a simple example using ZAR which is a common format for chunk data. So what imports are, this data should be created. So if we get here, you'll see that I am reading this data. This data is already chunked. And I'm seeing that, okay, the chunks are about 5 megabytes. And then I'm seeing that I have 33 tasks, 32 chunks. It's not too big. So in this case, yes, the chunks are a little small, but we're like also working with a smaller data because we're in Binder. I believe like if you're in your local machine, this should be a little bit bigger. You'll see different numbers. But notice that, yeah, this is, the array is like already chunked, and we didn't do anything when we read it. So let's try to compute the mean and then see how long this takes. Hopefully it won't be too long. So it's like 1.46 seconds. For those in your local machine, this should be a bigger, and then maybe it might take a little longer. So now let's load a different example, where on purpose we made this array to have smaller chunks. So I'm having like on the kilobyte kind of size now. Let's see what happened when I try to compute something that it has super small chunks. And now we wait. Hopefully this won't take too long. But the point being here is when we see this kind of problem, it's also see that here we have like 20,000 tasks. And we have like 20,000 chunks. This is kind of like saying, like, hey, this might be too tiny. It's like this graph is like way too big. Might not be great. Actually, a good thing would be to have the dashboard looking at this while we do this. I think this is still computing, so we can take a look. Oops. Can we do it in here? Oh, we need to do the, what was the, okay. So this is proxy slash, that should be, I think this might even still computing stuff. All right, we're doing stuff. But see, like, they're like super tiny. And they're like a lot of space in here, a lot of red going on. This is something that, like, if you see a dashboard is red, then you might want to think like, hey, what can we do better? This is like a lot of white space, and you see like these tasks are taking like so small amount of time, but then like, and then we're doing a new one. And let's just run again the one, I want to see, can we, yeah, that one might be short, but let's see how it looks, the dashboard on the one that wasn't that small. So let's do this one. Okay, so if you see, like, still some red over there, but it's like this took kind of like, it was pretty decent. So as a quick exercise, let's try to make this array the one that has like a super tiny stuff. Let's just provide a chunk size when we read it. So something like chunk size equals, and then come up with something that will make the compute of this mean look a little bit better on the dashboard. And then take a look, and then look at the dashboard, look at the time. This like took 1 minute and 30 seconds. So it's like, it's a big amount of time compared to 2 seconds. So let's do, I don't know, 3-4 minutes. Try to come up with something, play around a little bit, see how low you can get that number. From 1 minute, 30 seconds to something that is better than that. Yeah. Right. So the question is, are there any public attributes to get the number of tasks? Do we have? It's there, right? But like, can we? Maybe something like, let's do it on a dot. You mean? Yeah. What if we do length of that 33? Yeah, that's it. Great question. Actually, you know what? All right. Was anyone able to get it like run faster than, if you're in Binder, at 1 minute 30 seconds, but if you're in like your local machine, they should have been probably around 20 or a little bit less. Right. There are multiple ways of going about this, and then you can optimize and then see and then play around. One way of doing it is, we saw before that the original case had 33 tasks, 32 chunks, and we sort of kind of like have a hint over here on at least how to get it to the time that this first case run. So if we provide the same chunks than the original one, we can see what happens. So reading this, what I got, okay, we got 4 chunks. This might be something weird here. Something happened. Oh, it's because that one, the solution, I believe it's for the case that you're on your local machine, so something to fix, I think. There we go. So if we have our chunk size to be the same size that we have before, then let's see how long it takes. Should be ideally faster. All right, 5-6 seconds. And then now we are reading that and then like re-chunking things, so then it's not entirely the same time. But hopefully with this, yeah, you have a question? Yes, so yeah, you can use, like, you can read it and then use rechunk, or then when you are reading it, you can provide a chunk size, and then that will kind of like accommodate things. But yeah, either way, yeah. Fair. Oh, yes, absolutely. So there was a question from over here that if there's any way of getting the amount of tasks, but instead of like just running this and then reading it from it, it's like by executing basically some code. So a.dask will give you the task graph. And then if we do the len on that, we'll get, in this case was 33 because I was running on A. So this is this number. Yeah, absolutely. Yeah, it's the number of tasks that the scheduler will be like sending to the workers. So now we play around with a lot of arrays, and in general, like we won't be creating our own arrays, and we're going to be reading from somewhere, and in some cases, like we will be reading data that is data that has like, I don't know, many dimensions. And for that case, there is a good library called Xarray that allow us to kind of do this mix between arrays and pandas data frames. So for example, we can label those dimensions and then work with that. Jacob? Yeah, that would be great. I think you know more about it. I can go through this, but there's going to be a whole tutorial about this, but this is like a quick peek on.
Yeah, this is like a little sneak peek at Xarray. I've used Xarray a bunch, but I'm not like a super expert. But Anderson is there who can like interrupt me and tell me that I'm wrong in things that I'm saying, which is helpful. So yeah, but if you're interested in all the arrays you've seen so far are like just bare arrays of numbers, right? But if you have data which has other arrays that describe each of those dimensions, like you might have air temperature data, like we're going to open in this example, where you have latitude and longitude and time, and those dimensions have that associated metadata is important, right? Like the values of the time axis is something. So you have an array with other arrays that describe the axes of that. And Xarray is a really great tool for working with data in that kind of format. I've used it a bunch in weather and climate. I've seen it used all across geosciences and in other places too. So let's import Xarray. We can use the open data set from the tutorial to open up some air temperature data. Now Xarray uses Dask under the hood for its array representation. You can use just NumPy as well, right? But I think by default it will do Xarray on, it will use Dask on data sets like this. So if we open this data, we'll pass it some information about how we want it chunked or how the chunks are, and we can have a look at this. Xarray's also got nice representations in Jupyter to try and make it a bit easier. So you can see we have this array with these dimensions, latitude, longitude, and time. We can kind of see all the information. We can see the values from these descriptive arrays. And we can see the kind of data variables. So this is just it has one variable of air temperature, but say you're loading like the output of a weather model, you probably have a whole load of variables, right? Wind speeds and temperatures and humidity and all that kind of stuff. So you can have like a whole load of variables here. So you've got this like high level description of this data set and what's inside it. But kind of as you start digging into it, we can see, if we just have a look at this air variable, it is a Dask array underneath, right? So Xarray is leveraging Dask to do the NumPy-like operations, but Xarray gives us like this nice API on top. We can see the shape and size of this. We can see the Dask chunks and all that kind of stuff and the tasks. This is just a Dask object underneath. It's wrapped up in one of Xarray's. Xarray's adding a bit more descriptive stuff, but it's just like plopped the Dask representation in the middle there, which is neat. And we can have a look at chunks as you would with a normal array. You can use the same operations to kind of inspect down into those. But then we can do some kind of more like domain-aware operations, right? So we can say, I want to take the mean of the air temperature across the time dimension, and because we've got these labels, because we've got this descriptive information, we can calculate that mean. But again, this is a lazy Dask operation. It's calling down into Dask, and it will give you back a lazy Dask object. And so this ran very quickly. It didn't actually take our mean, and it's showing us in order to calculate the mean, we would have to calculate this Dask array. So if is the dashboard still alive? Yeah. Let me just open a dashboard plot so we can just see something. So if I just call load on this mean, oh, that was not the most exciting of graphs, but you can see it did a Dask graph operation here, and it gives us back the result. And this, you might recognize, is a NumPy representation now. Now that we've computed the result, it's kind of filtered it all the way back up. But it's still wrapped in this Xarray context, right? It's still got all this rich metadata from Xarray's perspective. Now, Xarray is built on top of NumPy and Dask Array and gives you, this view onto multidimensional array data sets. But I think one of its core goals is to give you a pandas-like experience of working with your data, right? So you can do things like group bys and selecting and all that kind of filtering stuff that you would do in in pandas, but you can now do it on like multi-dimensional data sets. You're not working in tabular data here. So let's just pull out the air data array. Right, so you have like a data set that contains all of our things, and then we have our data array, which is each thing within that. So we'll just pull out a reference to that there. We can do, we want to group our data by month, and then take a mean across time, and then we can subtract that from the original array. And again, we build up this Dask operation. We can see like the final result is this one-dimensional array. And then we can call .load, which is kind of that, calling .load in X-ray, we'll call .compute underneath in Dask. If we run that, again, we can see X-rays doing things there, and we get our 1D array out from there. You can see there was a bit of chit-chat between workers as they were loading data around, moving and doing tasks. But these are all kind of array operations under the hood, doing our group by. We could also do like a resample of our data. The thing we've just calculated, we could resample it onto like a 1 week sample size, and we can take a mean across time and a standard deviation across time. And then we could plot that, right? X-ray also, one of the things I used to find particularly useful when I use this day to day is this .plot function. So if you've used .plot in pandas, right, it just generates sensible plots for you based on the data you give it. Obviously, you can tweak and configure it and however you like, but X-ray has that same ability. So if you have an array with scripted metadata, you can call .plot, and Dask will get busy doing some stuff, and then you'll get out your matplot, libplot, or bokeh, or however you're configured. So that's just like a small taste into how we've started with this like low-level Dask thing that's doing these kind of out-of-core operations, these lazy operations, that allows you to scale, and then you're building up to domain-specific tooling on top of that. If this is interesting, if you like the look of this, please do go to the X-ray tutorial this afternoon. That will cover this in much more detail. So yeah, that's the end of the array notebook. Do we want to go straight into the delayed one, or? Perfect.
Thanks, Chico. Okay, I double checked too, and the len of the Dask is truly the number of tasks for sure. So we just wanted to make sure that it wasn't just the top level or something. Okay. All right, so moving on to Dask Delayed. So Dask Delayed is one of the lower level interfaces into Dask. So we had this analogy of like Dask Array and Dask DataFrame being like ready to wear clothes, like a pants or a shirt. And Dask Delayed is more like the cloth that you can use to like sew your own clothes. So it's one of the really powerful, but like a little less like, it's just like a powerful building block that you can use to construct more advanced functionality in Dask. So in that, we don't really need this isn't going to be very intensive compute. It's more showing how it's set up. So if you don't have data, if you don't have an array or a data frame, maybe your data is some other structure that's a little weirder, that doesn't naturally fit into one of those paradigms, delayed can be really good for you. Because delayed is much more about the functions rather than about the data. So you can use delayed to decorate functions so that you create the task graph as you chain together functions or as you construct these different operations. So it can be, if you have a pre-existing code base that's very function heavy, it can be that using Dask Delayed can be a really straightforward way to just parallelize your code base. It's a bunch of documentation. And let's start running through. So here's a typical workflow kind of sketched out that might be good for delayed. So the whole point of it is to process a bunch of files. And there's like you read a file, you do a transformation, maybe that's like changing the units or whatever, flipping it or something if it's image data, normalizing it in some way.
and then maybe you write it back out to a different file path. So that can all be summarized in one function. And then you have this for loop where you're iterating over all your files and you're doing this processing to them. So if you have this kind of pattern in your code base, this can be like one of the things that's really good for Dask Delayed, because you don't have to worry about what the data really looks like. If you already have the functions that operate on your data, you can just pop. Maybe this is even hard to notice, but you just pop this Dask Delayed decorator on that wraps your whole function in Dask. Basically, it's like a Dask cloak or something. So here we're going to set up these super simple little functions to just show how this works, the mechanics a little bit. So there's, and if you look at the Dask talks, we do this all the time to show how Dask Delayed works. So there's these functions that are total toys. There's an increase function and an add function, and they both have some sleep in them to just make them take some time, so we can see how the timings change on these things. But that's just a way of demonstrating how delayed works. So we'll set up these little functions. So far, these are just normal functions. They don't have any daskiness to them. They're just regular Python functions. What's this one? Restart the kernel. Refresh the page. All right, so we start by, let me just get my client. Okay, so we created these Dask functions, or these simple functions, no Dask. So now we're going to take these functions. We're going to do use the increase function twice to get an x and a y, and then we're going to add them together. So, and we're going to time this. The important part is timing this so that we can see how the timing changes. So if you think about this function, we can develop an expectation, right? It's going to take 3 seconds because we're doing the increase. It's going to take 1 second, another increase, another second, and then we're going to add them. So it'll be 3 seconds because the actual operation takes no time. And then in this one, we're going to add this Dask Delayed this decorator, and we're going to, so that'll make the functions lazy. So it's just constructing a task graph now. So we declared those functions, and then here we are, we're setting up the task graph. So it takes no time, basically, because we haven't done anything. And then once we call .compute, we should have set our expectation before so we didn't get the answer revealed. But basically, the increase can happen at the exact same time in parallel, and then the add happens afterwards. So it only is going to take 2 seconds, basically, because it has one of the seconds is happening at the same time. So we can look at this Z, and we can see that it's a delayed object. So before we've been looking at DataFrame objects, array objects. Delayed objects have a lot less metadata that we know about them, so we can't have a pretty representation because Dask doesn't know that much about them. They're just holders, basically, for the graph. So we can visualize them, though, and this is one of our little task graphs. So we can see the 2 increases that happen at the same time, taking 1 minute, and then the add. So we talked about how we went from 3 to 2 seconds. You might have noticed that we didn't actually go to 2 seconds. We went to like 2.2. There's some overhead that Dask is always going to take to do this setup and scheduling. And we can't go down to 1 second because the add needs to wait for the increases to be done. So you can't parallelize the increase, add all at exactly the same time because it needs to wait for the inputs. Okay. So this is just an example of parallelizing a for loop. So we have this data, and we're going to be running this increase function over all of the items of our list. And we're going to be using these Dask delayed, increase, and sum functions to parallelize. I'm realizing now that I've redeclared the increase and add function. So this isn't actually serial, but sequential code. So this is actually already decorated. So it's oh no, I'm redeclaring them here. Okay. Okay, so this is good. So this is a sequential code. So it's going to take whatever 10 some 10 plus 2 or something seconds, and then we can get the result. Okay, so we're gonna. I guess I'll let you guys work on trying to make this into a Dask delayed type thing. So I'll give you maybe 2 minutes to work on that. You probably will, this is a hint, you're probably going to redeclare the function. And if you have questions too, that's okay. All right, I'm going to go ahead and reveal the solution. So the only thing to change really is to add Dask delayed to the increase function. And that should allow your data, all your increases to run in parallel. And I should have put a time on this so we could see the difference. So you might notice that you don't have to parallelize the sum because all of the inputs to the sum are delayed objects. So that'll just work correctly. Like once you only have to add delayed to functions that are taking like non-Dask inputs basically. So that takes 2 seconds down from our 8 seconds before. All right, so this exercise is to parallelize a for loop where some things are delayed. Some things are Dask delayed objects, and some things are sometimes are necessary to know what to do next. So some things you want to happen immediately, and some things you want to be lazy. Some functions are really fast to run, and it can be useful to do those immediately to determine which functions to run next that are potentially slower. So this is like part of something that you're always kind of thinking about with Dask of what do you need to know immediately versus what can wait, and that's part of the intuition that you'll develop as you work with Dask. I can leave you to. I'm going to skip that one because it's less interesting and go right to Pandas group by reduction. So you can go back to that one later if you want. But in this one, we're going to read some CSVs. This is like similar to the Dask DataFrame section, but we are going to be using Dask Delayed to use Pandas directly. So we can look at these DataFrame these CSVs that we've collected, and we can use pandas to read one of them. So this is all pure pandas stuff. So in this case, what we're trying to demonstrate is that in this case we're using pandas, but it doesn't have to be any type of object that has a special relationship with Dask. So we're not using Dask DataFrame. So this could be any type of object that you might have, like some special objects that you create in your content area or your area of expertise. So we can look at the data types of the pandas object. When we can start stepping through the different things that you can look at about this data, like the origin, and you can look at these are the types of things that we've been doing on the pandas data on the Dask DataFrame notebook. We can also just do raw on the pandas DataFrame. And we can, so in this example, we're going to be using the pandas DataFrame, iterating over each of the files and getting the group by, getting the mean departure delay per airport. So this is pure pandas code that we are running, and you can see how long it takes. So we're going to read in the file, we're going to do the group by, do all the pandas stuff, collect up our results, add them all together to get the delays per airport. And this takes some time. For Dask, for delayed, you can use delayed to parallelize that code without using Dask DataFrame. So you can use Dask. I guess I'll let you work on this one. So we're going to be, some things to keep in mind are that you can wrap the functions with Dask delayed, and the output of that function is going to be a delayed object. That delayed object you can then operate on. We can do slicing, you can do method calls on it, and those will chain together to make a delayed, to operate in the right order to have the output also be a delayed object. And then when you're done with constructing your graph, you can call .compute on it to get the output. And if you want to get multiple outputs, you can use Dask.compute to get the outputs of like multiple different delayed objects. So this is the sequential code. The key here is really to figure out like which of these functions is important to wrap in Dask delayed and which can be left unchanged. So in this case, the only function that you really need to worry about is the read. So you can write a custom function that has the Dask delayed decorator that reads in the file. And once that file is read in using this particular function, it'll the output will be a delayed object. And anything after that, anything you do after that will just operate on the delayed object. And that's all you need to do to get this thing to be a Dask graph. Because you can see, like, after this point, all the next things that we're doing in this for loop are just methods off that object. If you had some other function that was operating on, even if you have some other function that's operating on the objects, that should still work. And then you can construct the graph and call compute, and then you'll do, you can visualize it. So this is the visualization of the task graph that we've constructed. I'm not using the fancy new one, so it's just a lot of scrolling. But you can see if you scroll enough that you see all the read files, and then the group bys and the get adders, and all these tasks are how they chain together to eventually get the result. So this is more of like a tree style. So you'll notice that here I used Dask.compute rather than, so when you have a number of delayed objects to work on, you'll use Dask.compute. The output will be an iterable, so here I'm just plucking off the first item in it. Yeah, you can do that so you can look at when you want to call .compute and whether you want to call it on the intermediary values. Basically, anytime that the output is going to be relatively small, that's an okay place to call .compute or .persist, because then that data will be, for compute's case, it'll be brought into memory. For persist's case, it'll be brought all the way into your notebook. And for persist's case, it'll be stored in the futures objects that we will talk about more later on. So when to come out of Dask and all the way back into like real evaluated results is something to sort of tweak if you're developing Dask workflows. And here there's just some more questions that you can consider. And then there's a bunch of links to the delayed information. And we'll be talking about more of the lower level ways of constructing things with these low level Dask APIs in a future notebook. But for now, let's take a 15-minute break, and we'll come back. We're going to talk a lot more about deployment and distributed clusters. So hopefully that all the dashboard stuff and all the client creation that we've been doing will make more sense then.
Right, let's get back into it, everybody. So, oh yeah. Yeah, I think I can hear myself, I think.
Yeah.
Cool. We're nearly there. This is like the home stretch now. I appreciate these tutorials are long. We've got about 45 minutes left. We're going to dig into distributed and futures after this. So like, everything we've done so far has been around using Dask, using the API, making use of it from like a Python perspective. And we've dug a bit into the dashboard and things, I guess, but we've glossed over the cluster creation a bunch. And now this is the time we're going to kind of come back around and say, where are these processes coming from? How is this scheduler alive? And I think one of the things that we've done in basically every single notebook is we've called this cluster object. We've created this cluster object, and then we've not really talked about it again. I've kind of just moved on with what we're doing. So let's take a step down into the deployment side of things and look what that is. So the way that Dask handles dispatching work to a cluster is by having a client object in existence in the global scope. So you don't have, when you call Dask.compute, you don't have to tell it where the client is as long as you've created it, as long as it exists. And in basically every example so far, we've just created that without too much config, right? We've either just created the client object and instantiated it, or maybe some of these options have been doing like n workers equals 4 or something. But we've just created this client, and we've not worried too much about it. Now, Dask tries to help you in these situations if you don't give it too much information to go by. So by just creating an empty client, it'll immediately go, right, I'm going to go and connect to a cluster. It will check your config and go, I don't have any config. I don't know if there's any cluster. I'm just going to make one. And so it'll create a cluster for us, just leveraging our whole machine. And it'll kind of pipe everything through. The keyword argument actually that we're passing to client, the NWorkers one, the client doesn't know what to do with that, so it passes it down to the cluster that it creates for you. You can change these defaults if you want client to automatically create other cluster types if you like. But let's kind of have a look at what that manual process would look like if you were going to create a cluster yourself. So instead of just instantiating client, we're going to import this object called local cluster, and we're going to create one of these before we do anything. So we have this class, local cluster. We're just going to instantiate it and create this cluster object. And hopefully the representation that appears is familiar, right? This is, a lot of these representations we have of cluster objects get nested within each other. So this is the cluster level view onto a cluster object. So we've explicitly said, I want to create a local Dask cluster on my machine that's going to leverage my whole machine. I haven't given that any config, I can do. But this means it's going to inspect my environment. It's going to see how many CPU cores I've got. It's going to see how much RAM I've got. It's going to make some decision about how to carve that up. Dask will create workers, which are kind of contain many kind of threads that can do things, and it will kind of make a decision. I think if I ran it on this laptop, my laptop's got like 12 CPU cores, and I think it creates 3 workers with 4 cores each. That's just kind of a thing that Dask does to try and balance the best performance it can. It's just numbers that we've got from benchmarking and things. But by creating a local cluster, it'll inspect your environment, it'll create a cluster, it'll start the workers. We can see the scheduler that gets created here. We can see the workers that get created. All of this has been done for us by this local cluster object. Now, because we're seeing the representation at the cluster level rather than the client level, we get some extra fancy widgets here. We've got a little scaling tab that we haven't seen before, which doesn't do anything because I can't scale my laptop and make it more powerful. But as we move on, we can see if we are able to ask for more resource, Dask can do that either manually or intelligently for you. But what I kind of want to show here is this concept of creating a cluster by importing a class and instantiating it is a theme that comes up all the way through deploying your Dask clusters. Now, if we have a look at the local cluster object, we can see we can configure all sorts of things about our local machine. We can say how many workers we want and how many threads instead of letting it do auto-detecting. We can tell it what IP address to listen on, what ports it should be using, all that kind of stuff around what the scheduler should be doing. We can set that up here. And all of these configuration options that we pass to the cluster manager will vary from cluster manager to cluster manager because setting those things explicitly about my laptop doesn't necessarily translate onto I want to launch a cluster on an HPC system. There are different options. So although we're going to be instantiating classes all over the place, often the documentation says insert your configuration keyword arguments here, and then it kind of documents what those are. Often this is like, what credentials do I need? What if I'm launching on an HPC, what size should each job allocation be, and all those kind of settings. If you're launching on the cloud, what VM type do I want? Which base image do I want to use? All sorts of configuration options. So check the documentation on each kind of implementation. But once we've got a cluster object, they implement the same interface. We have this cluster interface, which is designed to try and make your life a bit easier in switching from cluster to cluster. It kind of makes life more straightforward when you are doing I'm going to start on my laptop and then I'm going to scale to a server and then I'm going to scale to a cluster. And as you're shifting your workflow, you have this cluster object that you can work with and use. And you can interact with it in very similar ways. So some of that kind of stuff is we can call get logs on our cluster object. And this will give us, there's no local logs for this one, but if you click on the scheduler, this is the kind of standard out from the scheduler process. You click on the workers, you can see the standard out from the worker processes. This is really useful for debugging. Remember ages ago I was talking about the dashboard showing you big black bars when things go wrong. When things go really, really wrong, these logs are the place to look for the worker that's actually died and really couldn't do anything. You'll get the full Python tracebacks in these logs. This is a great place to come and find that information. And you can kind of drill through all of those. The cluster's also got information about where is the dashboard. Where do I find that? It gives you the link. If you just look at the dashboard link property, we like reuse this in the various like widgety components. But I was just chatting to somebody during the break about it's pretty common if you are going to write a Python script that's going to use Dask and you're going to launch a cluster, you might import local cluster or whatever kind of cluster, instantiate it, and then print dashboard link, and then do your work. So if if it's a long-running script, you can look at the logs, you can find the link to the dashboard, you can open it up, and you can watch the progress as your script is running through. Right? You can kind of get that information out of it. And then once we've got this cluster object, we need to tell Dask to use it. And so we can instantiate client objects and just pass it the cluster and just say like, here is a Dask cluster, use it. And so this is kind of equivalent. What we've been doing so far, I guess, the like lazy way of doing things, is equivalent to doing this, where you're kind of instantiating a cluster within the client. But you can just pass the cluster object straight through to the client. If you create that, the client will connect. It will use that cluster. You can see the cluster type is this local cluster. And it's wrapped up this representation that we've had before. But doing things this way, creating a client and then creating the cluster and then passing that to the client is like a pattern that will become familiar if you're using different cluster types because, oh, I want to switch to using a Kubernetes system now, so I'm just going to import kube cluster and create a kube cluster object, and then I'll pass that to my client and carry on as normal. Now, before I keep going with that, let's actually dig a little bit down into like what was local cluster doing. So local cluster is creating this scheduler and these worker processes for us. And then it's just making sure everything's kind of talking nicely. But we could go really manual and set things up completely like bare bones if we want to. And I'm just going to do that. If I open up a terminal here, that green is not pleasant, but if I open up a terminal, I can run Dask scheduler. Okay, now I have a scheduler. And this scheduler has decided that it's listening on this port. It's using the default port. If you start multiple schedulers, you'll get, 8786 will be busy, so it'll just choose a different random high port. So this is the place to come and look for that address. And then, I could open up another terminal. And I could say, I would now like a Dask worker, and you should talk to that scheduler. Here's his IP address and port. And we should see over on the scheduler side, it receives an incoming connection from the worker. This is like the most bare bones way of creating a distributed Dask cluster. You start the scheduler process, you start the worker processes, however you do that in whatever environment. And then, we have this address. I could come in my Python session and let me just delete those. If I do client equals client, I can just give it this string address as well. Client will be perfectly happy with that as long as it can find the cluster. So I can connect a client directly to a scheduler that I just started on the command line. This is like a pretty common way to start clusters up if you're like playing around or want to try stuff out or if you're developing Dask. So this is kind of what's happening under the hood. When we instantiate this local cluster object, it's doing a bit of inspection into the environment, and then it's just trying to start these processes for you. It will start the scheduler. It'll then figure out what that scheduler's address is. It'll start the workers, give it the address. Everything should be talking to each other. So what are the requirements, I guess, for running a cluster like this in terms of like connectivity? I'll come on to this a little bit more in depth, but it's worth saying at the moment. I ran scheduler and worker here on my laptop, or in this binder environment, I guess, and they can talk to each other. But the scheduler is going to listen on these two ports, the dashboard port and the communication port. When we start the worker, that is going to try and connect to the scheduler's communication port, and it's also going to start its own communication port. If we start lots of workers, they'll all be listening for traffic, and they'll be talking to the scheduler. And when we saw those red blocks in the graph where the workers are talking to each other, they will open kind of ad hoc connections to each other, to that communication port, to just say, here's some data, and it'll push it into another worker, or it'll pull data from other ones. They can steal work from each other and do all that kind of stuff. So in order for all of that to happen, we don't know what these random high ports are. They're going to be assigned. So the scheduler and all the workers need to be on the same network, effectively. There shouldn't be any firewalls or anything restricting traffic between them. I think in the docs you will find the high port ranges if you do need to poke holes in firewalls and things. But then from a user perspective, the client will only ever connect to the scheduler on whatever the communication port is for the scheduler. So if you're trying to start a Dask cluster inside some other systems, some HPC systems and cloud system. Everything will happen kind of internally between the scheduler and the workers, and then the client just needs to be able to poke through to speak to the scheduler to kind of give work and get results back. So you can often set up configuration rules, you can use SSH port forwarding, you can do whatever you like as long as your client can talk to that scheduler. So that's like a very manual way of doing things, but hopefully that's given you like a bit of an overview of what these processes actually are. Now, these scripts are just, these are just Python like entry point console scripts or whatever. These are just Python libraries you could do. Instead of doing Dask scheduler, I could do like Python -m distributed.cli.scheduler, I think. Maybe not. Is that right? Maybe it's Dask scheduler. Yeah, okay, so it is just a Python process. So in order for all these things to talk to each other, you have to have Python in all of these places. You have to have the same version of Dask pretty much installed in all of these places. You can get away sometimes with minor version differences, but I just recommend you don't because it's a headache. Just make sure the same version of Dask is everywhere. And then when it comes to actually executing your graph, you're going to be doing stuff in the client, importing libraries, using them, leveraging them to build up these graphs. And then the graph is going to be handed to the scheduler. That's going to be handed on to the workers, and they're going to do stuff. And as part of that doing stuff, they're going to import those same libraries and do those same things. So ideally, the Python environment is going to be identical between where your client is being created and where the workers live. So I'm doing this on my machine, but if I was going to SSH to another box and start the Dask worker process, I would want to make sure I've got consistent Python environments between those two places. Again, you can get away with like some minor differences, but it'll cause you a headache most of the time. So when you connect a client to a cluster, it does do a version comparison, and it will print out a warning table saying, I found that you've got this version of NumPy here and this version of NumPy here, and they're not the same. Sometimes it will tell you whether that's like a warning or whether it's critical, but generally just try and make sure they're exactly the same, and you'll have far fewer headaches when you're working with this stuff. The other thing I try and say as well is try and make sure the scheduler has the same environment. This is less important, but occasionally the scheduler will deserialize things as it's passing through. It's very, it's rare. It shouldn't happen really, but we are kind of shifting back more in the direction of using Pickle as part of passing things through, and it does mean things get deserialized more often, which just means if you're missing dependencies in the scheduler, you can get weird errors. So I just try and say to folks, just have a Conda environment script or something that sets up your Python environment. Make sure it's the same everywhere. It's much easier on like HPC or something where you might have a shared home directory and your Python environment can just live there. But it's just much easier if you've got a consistent environment around. So instead of creating stuff manually on the command line, because that's tedious, we have all of these cluster managers that will create various clusters of various types for you. So the most popular one that we see coming up in the Dask survey that's used a bunch, which is kind of fun because it's like not the most sophisticated, but it seems to be like one of the most useful, is SSH cluster. So you can import from the Dask distributed core package SSH cluster, and then you instantiate it like you do a local cluster, but the first argument you give it is a list of host names. And those are host names you should be able to SSH to without having to do any manual password putting in, so you should have keys set up or whatever. But if your machine can SSH to those other machines, when you instantiate SSH cluster, it will open those SSH connections. The first item in this list will get the Dask scheduler command. The rest will get the Dask worker commands. It's a really neat way. Like, I don't know, if you've got colleagues with workstations that they're not fully utilizing that you can SSH to, I used to do this a bunch, just use SSH cluster and just grab a bunch of desktops, pull them together into a nice little ad hoc Dask cluster. Hey, it happens all the time. It's great. Also with like servers, if you've got big beastie servers or something, this is just a nice way of like reaching into it and starting your processes automatically. There's a whole bunch of configuration options you can set around the SSH connection itself, but ideally, if you can SSH without a password, then this will work for you. It will look for Python in the same location that Python is currently running, the process that's running this. All these things are configurable, but SSH cluster is like a very useful way of getting started, like exploring outwards from your machine. But both of those examples, the local cluster and SSH cluster are what we call like a fixed size cluster. Right? My laptop, I can't change the shape and size of my laptop. And for SSH cluster, I've given it a fixed list of host names. Those are the machines that will make up my cluster. But we also have a whole bunch of cluster managers which can talk to some kind of other resource manager and ask for allocations of resource. And if we can do that programmatically, if we can speak to something and say, can I have a machine, that means that whilst we're running calculations, whilst we're doing work, we could speak to that again and say, can I have more machines? Or we could say, oh, I'm not using these. I don't need these machines anymore. And so Dask can scale up and down. Now we can do this. I haven't got any huge examples in here because all of these require some kind of resource manager, and it's a little tricky to show in Binder. But we have cluster managers for Kubernetes, for Hadoop, for all sorts of cloud platforms. We have stuff that either leverages VMs or leverages like container-based platforms. And we also have Dask Job Queue that will use resource managers like PBS and Slurm, SG, whatever you kind of have. Yeah, good. It's just SSH is enough. The idea, I guess, with all of this is that we can just, Dask, from your laptop or wherever you're running this, it can just reach into other systems and start the processes that it needs. I often enjoy when you do that and then you use another tool like XGBoost with its Dask integration, because when you have Dask workers and you use XGBoost, it will ask the worker to start an XGBoost worker and like create a cluster. So you're kind of like reaching into all these resources and then like stacking clusters on top of each other to this like nice high abstract level of, I don't know, compute stuff. It's fun. But yeah, so all of these cluster managers can reach into these various systems. So for Kubernetes, we can ask for pods. On Hadoop or a job scheduling system, we can ask for allocations. On cloud platforms, we can ask for VMs or containers or whatever your unit of currency is. Some of these will require you to provide a Docker image to run, say as a containerized platform. It will ask you to provide some kind of config for the VMs that are going to be launched, or whatever that kind of thing is. You have to set it up a little bit, and the network constraints kind of apply. But once you're in this state where you can instantiate Kube Cluster or EC2 cluster or whichever one of these cluster managers you want to use, if it can create one allocation, it can start the scheduler, it can create more and start the workers, and then you can do things like calling cluster.scale and just give it n number of workers that you want. And this will just create more allocations and start more workers and they'll connect in. So you can do this at like fixed points through your script. If you know you want to run something on one worker for a little while and then you want to burst out for a little while and then you're going to come back, this is a great way to do that manually. But Dask is aware of what's happening, right? We looked at that profile before that was like, this is how long each of these function calls is taking within your code. And so the scheduler knows how long these things are taking. As it starts running tasks through, it's got the timings of those tasks. And so it can do some quick maths and say, if I was going to run this whole graph in 5 seconds, how many workers do I need in order to get through all of my things? And so we have this other mode called adapt, where you basically say to it, try and do it in 5 seconds. It's up to you to go and ask for more resources when you need it. So Dask basically starts auto-scaling as it's working through the graph. So if the graph is kind of stretching out, it'll start asking for more resource. If the graph is reducing, it will give up resource. It's like super nice on resource managers that have very fast allocation, like provisioning. So I've used this a bunch on Kubernetes, where it's like sub-second to get a new container running. You can have like many folks working on a cluster of 50 machines or something, and they're doing these like really bursty auto-scaling workloads where their Dask graphs are like bursting out, grabbing resource from within the Kubernetes cluster. And because you've got all these bursty workloads, you kind of like averages out and you get folks being able to grab way more resource than they would normally be like quoted. And they're kind of balancing out how that resource is being used. And then if you're using Kubernetes on the cloud or whatever, when the Kubernetes cluster hits its limits, it could start auto-scaling and asking for more VMs and doing all sorts. We used to see clusters of machines that would, the Kubernetes cluster would be at a few VMs in the morning, folks would start logging in, they start running Dask work, and the cluster would start scaling up, and it would kind of hold steady as folks are submitting all this work. Lunchtime, it might start chunking back down again. You can do a lot of fun stuff with like saving money on cloud allocations and doing stuff automatically. But I guess one of the things that we've not talked about hugely here is that every single one of these Dask clusters that we've played around with has been really ephemeral, right? We've just created this Dask cluster and then it's gone again. We've started it, we've deleted it, which makes sense when it's processes on a laptop, but that can be more challenging when it's like, well, what if these are VMs in AWS? Like they take many minutes and they cost money and like, maybe I don't want that to be ephemeral. So we do have other tooling for launching kind of fixed size clusters or clusters that are going to be like slightly more permanent. We're like trying to move from this place where we have some tools for fixed clusters and some tools for ephemeral clusters, and we're trying to push in a direction where you can kind of make these decisions a bit more ad hoc. But yeah, things are not quite there with that yet. We also have Dask Gateway, which is like a centralized like job launcher. So it's a bit like Jupyter Hub if you've used Jupyter Hub. It can launch Dask clusters on your behalf. It can proxy traffic through, and it can do some authentication and things. So that's quite a useful point if you want to like provide Dask as a service within an organization. Dask Gateway is a cool project. Now, I knew I had stuff on this. Anyway, let me skip over that. The last thing that I want to go over, because we still need a bit of time for the future stuff, is let's talk a bit about security. So all of the connections that we've made so far between the scheduler and the workers has just been speaking like raw TCP to each other. You could just listen to that traffic. You could, intercept that traffic. You could do whatever, right? This is unauthenticated stuff. So Dask also has TLS support, so you can encrypt any connections going between any of these components. If you're running Dask on an untrusted network, you can generate certificates, and the client, the scheduler, and the workers will do like mutual TLS authentication between each other, and then it will use those certificates to encrypt traffic going between. Some of the cluster managers will do this for you. If you use like any of the cloud ones and you expose the cluster to the internet, it will automatically turn TLS on. There are like performance downsides to doing this, but you can also do it and play around locally. You can see this little example. I'm using the Python interfaces to create a scheduler, create a worker, and create a client, and they're all using this set of temporary credentials that I'm generating on the fly, but you could also use some other certificate manager or generate the certificates yourself. So if you're interested in like authentication of your Dask cluster, have a look at this and the links out from here. And then the last thing to kind of cover is we do have other protocols other than TCP for communicating between things. You can use Unix sockets if you're on a Unix-based system to do like process communication without going through the network stack, which can be great if you don't want to burst beyond one machine. We also have WebSockets if you have like funny limitations around how you can proxy traffic out. Some HPC systems will only let you proxy web traffic or layer 7 traffic, and so WebSocket mode will let you proxy that out. But then if you're on like a high performance system with InfiniBand or NVLink or some kind of fancy network architecture, you can also use UCX, which will upgrade your network connection between workers to use cool hardware like InfiniBand and use RDMA to do memory transfer between workers rather than going through the CPU and the network stack. So if you're on like a interesting HPC system, I would check out UCX and the documentation there. But that's it. I'm going to kind of stop talking about deployment of distributed here, and I think Julia's going to come back in and talk a bit about futures and how they kind of live out in the cluster.
Probably if you have like super specific deployment questions, maybe just find Jacob. Yeah. All right. So the last notebook we're going to talk about is, we're talking about futures here. So futures is another, similar to delayed, it's a way of operating on, creating task graphs and running distributed computations. But instead, most of the things we've been talking about so far with Dask DataFrame and delayed and array, they create task graphs and then they wait. With futures, they start this, you submit the task immediately, and Dask, and it will return something immediately, the futures object, but the computation will be asynchronous. So it will just start happening when the resources are available and when it knows when the inputs arguments are computed. And it will just run while you're setting other things up, while you're doing other things. It runs in the background and returns. So you can keep track of these little futures objects, they'll have a status of finished or pending or errored, and then they have a result where the actual data is. So if you're familiar with concurrent futures, it's Dask's equivalent of that. So it provides real-time execution, but it can be parallelized and non-blocking. So the important difference between a lot of this code is going to look a lot like the delayed code, but the important difference is that futures starts immediately, and delayed will just wait until you tell it to compute. So for futures, you always need to be using distributed. So it needs the client object to be instantiated. So this is the same setup that we talked about in the delayed notebook of the type of workflow where futures would be a useful thing to use. So the difference here is that instead of decorating our function, we just when we go to run the function, we use client.submit. So we use client.submit, and I think we've sort of like hinted at this by using client.submit in other notebooks to just make something happen on the cluster. So client.submit takes these arguments, which is a function, and then like whatever arguments are going in that function. So here we've got this function process file, and then file name is the argument to that function. And it returns a future object that you can keep track of and look at the status of. So here's our little, here's some little functions that are not special in any way, just regular Python functions. We can run them serially like we always do, where we just can run one of them. And then we can also, the way that you would do this if you want a future is you do client.submit and then the function and then the argument. And this will return this object that has the status of pending, and it triggers the computation. Oh, I guess actually a graph would be nice here. Do our little trick. Cluster map so we can see things are happening. Okay. So when you do question to submit, now it's remembered it. I'll change the input. I'll just change it. So it should immediately trigger. So you might see that this little worker turned green for a second. So that was the operation happening. And then we can check after some time to see that now our future is finished. You can see the status changed. And you can check what the result is by doing future.result. So if instead of returning it right away, we just put result in here, then this whole cell would wait until the future came back. So that's how you can get the real value out. I feel like this happens to me a lot where I don't know that something's going to output a future, and then I've chained together a bunch of operations, and I end up with these weird errors. And so if you're running into weird errors where, if you do something like this, that won't work. But you have to call .result on futures. So there's other ways to wait if you have. There's other ways to wait for futures. So you can import wait, or you can get a progress bar that shows in the notebook that keeps track of how the computation is going, or you could explicitly wait and that'll block. You can also gather, instead of calling .result on one future, you can call client.gather to get the results from many futures all at once. So in Dask, there's often a dot method that you can call on the object, or there's a module level method or function that you can call on many things. So that's this equivalent. So you can also use instead of using .compute or Dask.compute, like we've been using in the other notebooks, you can use client.compute on any Dasky type thing. And so this is, for instance, a delayed example. You can use client.compute on that object, and the return will be a future rather than the real value. So you can see that, or if you were watching, you could see that there are some little things started happening, and you can get the result. So one of the nice things about futures is the computation moves to the data rather than the data moving to the computation. So if you're running this in your local Python session, you never need to see the intermediary value. Dask never needs to see the intermediate values in the notebook. It can all stay out on the workers. Client.submit pushes all the arguments to the cluster, and it returns a future. Yeah, so it's similar to compute. It looks a lot like compute, but instead of in this example, we just passed an object, client.compute on an object. In this case, client.submit, it's a function and then the arguments. So here's this doing an increase and then the sum of those. And you can see that it triggers right away, but it returns the future, and then the result is just sitting there waiting for when you're ready for it. And the arguments to client.submit, they can be regular Python functions and objects, or they can be futures. They can be other futures like we have in here. The argument here is a list of futures. They can also be delayed objects, all sorts of different things. And Dask, the client will wait until those answers are known, those outputs are known, before trying to evaluate. So what we looked at .persist in an earlier notebook, and what that is doing is it's creating the futures for every partition, and then it holds that reference to that data, and the workers point directly to the data. So that's, yeah. So yeah, we can, futures are a good way to control intermediary values and make sure that we're not holding on to extra data. And there'll be, when you stop referencing a future, its value will be forgotten. So if you want to, you can like delete future Z, and Dask will no longer hold on to that data. So for passing data around back and forth to the client, you can use client.scatter to pass data out to all the workers, but it's always better to construct functions that themselves read in data from wherever it's stored, because that way it doesn't have to go through the client at all. So in Dask, like whenever the workers can do things for themselves, that's better than trying to do it in the client and then pushing it out to the workers. So here's an example of another case where futures can be really helpful API. So this is a task that sporadically fails. This might happen if you're dealing with input data that's like messy, or like maybe it's image data that has like, 1 in 1,000 will have like a weird extra, like a different shape, and that messes up your whole operation. Or if it's like a request that times out sporadically, then you can run. So that's more of this example. It's something that fails not based on the input, but just randomly, which I've just made by using random. So this will generate, if you run this enough times, like you'll hit an error occasionally. So this is an example of running it 10 times, and hopefully it'll hit the error. I think it probably will. So we can look at all those futures, and we can look at their status and find that some had errors. And then you can pluck off a particular future and retry it. And so I plucked off the number 1 future, and it failed again, but we can just keep doing that. And now you'll see that it's a subtle difference, but like I've been retrying it, and now it's now succeeded. So that can be a really helpful feature of futures. So there's more concise way of denoting that with Dask. When you go to use client.map or client.submit, you can pass in a retries argument to say, I want that, just if it fails, just run it again, however many times. And then in this case, also we'll need pure equals false to know that the input to the function doesn't totally determine the output. So it shouldn't cache it so aggressively. And if you run that, you'll see that it runs a bunch of times and it gets the result without failing. Whereas if you ran it without, if you ran it without these, it will probably fail. Yeah. So that can be a helpful way of using futures. So futures, there might be one of those cases where you'd want to use futures is just if you're used to this kind of, like if this looks more familiar to you than all the stuff we've been showing you so far, like you can go ahead and use futures. It's a common like map reduce situation. And if you're using concurrent futures already, like it might look familiar and it might be like actually the simplest entry point into Dask. The other reason to use it is that the intermediary results stay in the cluster rather than coming locally. So new operations can be chained together, and you can set up whole flows that are working in the background, but all your data is on your cluster and not coming locally till you need the like actual end result. So that can be pretty powerful. Whenever possible, it's good to move computation to the data rather than the data to the computation. All right, the futures one is short. So I guess we can do a little wrap up to sort of situate ourselves back in where we started. So we talked about the different parts of Dask. So the high-level collections, the Dask DataFrame, Dask Grid. We didn't talk about bag, but basically if you have lists or JSONs, you should look into bag. And then we have the low-level collections, which is the Dask Delayed and Futures that allow you to operate more on the functions and do things like just pure maps and for loopy type things. You can use those to create really customized workflows. And then we talked about the client, which is what we've been instantiating in all our notebooks, which talks to the scheduler. This whole thing is the Dask cluster that Jacob was talking about being deployed different places. And the scheduler talks to each of the workers, which are your units of compute. And then there's all these libraries. If I'm going to plug the X-ray tutorial again, which is happening this afternoon. And I will also plug the Dask SQL talk, which is happening later. I don't know if there's other Dasky talks. But, and then there's a Bird of a Feather, which is Thursday at 6:30 p.m. So if you're already using Dask or you want to hear about other people who are using Dask, that'll be a cool time to just talk with other people. And with that, I think we can do questions. If there are any questions left. Yeah. They have to be pickable. It's using pickle, is that, or is it using something else? Cloud pickle, I think. Yeah, Matt. Cloud pickle. Yeah. Yeah. Mm-hmm. Yeah, it's because random has some state. And so if you run it a bunch of times, you will not get, it won't like start succeeding because it'll cache. I forget if it's that it will cache the state of random or if it'll just cache the inputs and expect the outputs to be the same. It's that one. Okay, it's that one. So if you have a non-deterministic, or if you have a sporadically failing task like this, where the inputs are the same and it like might succeed or might fail, then pure equals false will make sure that Dask doesn't aggressively cache that, and try to be too clever. Like we want to let it run again so that it might succeed. Yeah, for Dask. A setting that will set everything to pure? Is that what you're saying? I think it assumes everything is pure. Okay. Yeah? Mm-hmm.
No, as long as you can just SSH to that host, and it has Python in the same place on the file system. So if there's Python that was fine, or we starting from wondering, whatever, I don't know, so it assumes the path is exactly the same. If it's not, you can set that as a configuration option. That's like pure.
All right. Well, if you have if more questions occur to you, find us. There's also other Dask developers here, so we're plentiful. You can find us.
I have a question.
What's up?
If I wanted to get a Dask sticker, where's a good place to do that?
I can give you vintage Dask stickers. So we changed logo recently, so I think if you want new Dask stickers, maybe NumPy has some. But we can put the vintage ones out here if you want to come and get old school Dask.
We'll try to find the new ones by the birds of a feather at the latest. So we'll definitely have them there. So extra incentive to come to that.
This might be your last chance to get the old one.
Exactly.
Yeah.
So, yeah. But no, thank you for paying attention for 4 hours.
Yeah.
Have a